we introduce the notion of economic mechanism. An economic mechanism is a tuple A1, AN, X, G, where AI is the set of actions available to player I. X is the set of outcomes. G is the outcome function mapping every action profile to an outcome. We focus on the notion of implementation that is central in mechanism design. Start from a set of n players, whose types are θ1, θn. Given the profile of types of the players, we aim at applying a social choice function. The function is the goal that we desire to achieve. The crucial point is that the types of the players are private information of the players. If players are requested to report their types, they could misreport the types, if misreporting is the best for them. In other words, since the players are selfish, when required to report their types, they will report their actual types only if doing that can maximize their utility. Otherwise, they will try to misreport the types, trying to maximize the utility. The idea of economic mechanism is based on that observation. Specifically, we design an economic mechanism A1, AN, X, G such that there is an equilibrium S star specifying the behavior of every player for every type, such that for every profile of types, the outcome function, when the players play the equilibrium strategies, return the same outcome of the social choice function. In other words, starting from a social plan, we design an economic mechanism that, when the players play their equilibrium strategies, leads to the same outcome of the social plan. Formally, an economic mechanism implements a social choice function if there is a pure strategy equilibrium of the game induced by the economic mechanism, such that the outcomes achieved by the mechanism are the same of the outcomes that the social choice function will return. Notice that the equilibrium may be of different forms, for instance in dominant strategies or by a Nash. A direct mechanism is an economic mechanism in which the actions available to each player I are given by a set of types of the player. Thus, each player can only report a type from the set of the possible ones, and the outcome function is a social choice function. A mechanism that is not direct is called indirect. Focusing on direct mechanism, we can define another concept that is central in mechanism design, that is the incentive compatibility property. A social choice function is incentive compatible if the direct revelation mechanism admits a pure strategy equilibrium prescribing that every player will always report the true types. In other words, a social choice function is incentive compatible when the corresponding direct mechanism implements the given social choice function. The verification that a social choice is incentive compatible is in principle easy. Given a social choice function, we need to design the corresponding direct revelation mechanism. And finally, we need to check whether reporting the true type is always the best the player can do. Consider the example of continuous voting with average allocation, where the utility of each player is maximum when the outcome is exactly the type, and then the utility decreases linearly as the distance between the outcome and the type increases. Focus for instance on player 2, but the reasoning can apply to all the other players. The outcome returned by the social choice function is a bit on the right with respect to her type. If the player can, by misreporting her type, obtain that the social choice function returns an outcome closer than her type, well, the player will surely try to do that. Suppose that the player misreports her type, communicating a smaller value than her true type. For instance, suppose that the true type is 0.5 and the player reports 0.4. Thus, the average returned by the social choice function will reduce and then will get closer to the true type of the player. And in principle, it could be exactly the type of player 2, corresponding to the best case for that player. So this social choice function is manipulable by player 2 when it is considered as a direct revelation mechanism. It can be easily observed that also the other players can manipulate the mechanism in a similar way. Therefore, this social choice function is not incentive compatible. Consider the example of continuous voting when the allocation is the median. In this case, obviously, player 2 will never misreport her type, given that the social choice function is returning the best outcome for that player. Focus instead on player 1. The only way with which that player can change the outcome is to report a type that is larger than θ2. In this way, θ2 is not the median, but the median will be θ1. But in this case, the outcome returned by the social choice function will be larger than θ2, and therefore it will provide a smaller utility to player 2. The same holds for player 3. Therefore, we have that reporting the true types is the best the player can do when the allocation is the median. So this social choice function is incentive compatible. Consider the example of auctions without payments. Here, the game admits dominant strategy equilibrium where every player reports 1. That is, every player misreports her type, communicating the maximum possible value. Indeed, every player will try to be the winner, given that she has no punishment if she wins the item. So the social choice function is not incentive compatible. Consider now the first prize auction. The winner, when the players report truthfully, is player 1. However, she can improve her utility by reporting a type a bit larger than θ2 and a bit smaller than θ1. For instance, θ2 plus epsilon, where epsilon is arbitrarily small. So even the first price auction is not incentive compatible. Finally, consider the second price auction. Here, the winner, that is player 1, cannot improve her utility. Indeed, the payment will be always θ2 unless player 1 is not the winner anymore. But in this latter case, player 1 has a utility of 0. So player 1 has no incentive to misreport her type. Consider player 2. In order to have a utility different from 0, player 2 must be the winner. But if she is the winner, then her payment will be θ1 that is larger than θ2. So player 2 will be charged of a payment that is larger than her value. The same holds for player 3 and player 4. So the second price auction is incentive compatible. We try to investigate the relationship between incentive compatibility and implementation. We recall that incentive compatibility property is related to a social choice function, while the implementation property is related to an economic mechanism. Now, suppose that to start from a social choice function f and design the corresponding data revelation mechanism, and then check whether truth-telling is an equilibrium strategy. Suppose that the answer is not. So we have that the social choice function is not incentive compatible. Since we cannot implement the social choice function by means of the direct evaluation mechanism, we ask whether we can do that by means of some indirect mechanism. Recall that, in principle, indirect mechanisms are more general than direct mechanisms. Well, the answer is not, and it is provided by the evaluation principle. That is, given a social choice function, either the function is incentive compatible, and therefore we can use a direct evaluation mechanism, or we cannot design any indirect mechanism implementing that social choice function. Here the statement of the evaluation principle. Given a social choice function, if there is an economic mechanism that implements it in dominant strategy equilibrium, then such a social choice function is dominant strategy incentive compatible. Here the proof. If an economic mechanism implements a given social choice function, there are equilibrium strategies such that these two conditions hold. The first condition states that the outcome returned by function g, that is the outcome function of the mechanism, at the equilibrium is always equal to the outcome returned by the social choice function. The second condition states that the equilibrium strategy S star is an equilibrium in dominant strategies. That is, strategy S star is better than any other strategy S for every strategy of the opponents, included those that are not of equilibrium. Now we focus on the second condition and we relax it. Specifically, we restrict this set of constraints. Obviously, if the property holds in the original form, it holds even when we relax this condition. The first restriction is related to the strategy S that we use in the right term of the inequality. In practice, the original condition is that S star is better than any other strategy S. In our restriction, we require that S star for type theta is better than any other S star of the same player, but with different type. In this case, denoted with hat theta I. Obviously, the set of strategies S star of every type at theta is a subset of all the strategies S. The second restriction is similar, and it is related to the opponents of player I. More precisely, instead of requiring the optimality for every strategy S of the opponents, we focus only on the strategy S star that are optimal for a type profile. This is obviously a subset of all the strategies of the opponent. Now we can write this new condition that is obtained from the second above condition once we have restricted the strategies as discussed before. In blue, we restrict any strategy of the opponent to only those that are optimal. In red, we do the same with the strategy of player I. Focus on the terms in orange. The first term holds since the argument of the outcome function g are equilibrium strategies of type theta I and theta minus I, respectively. The second term holds since the argument of the outcome function are equilibrium strategies of type at theta I and theta minus I, respectively. So we can substitute the outcome function with the social choice function, in which the argument are the corresponding types. Thus, we obtain this new formula that states exactly that the social choice function f is incentive compatible. Now, the central question in mechanism design is what are the social choice functions that are incentive compatible. that is the social choice function that we can implement in practice. The main result is negative, providing an impossibility result. More precisely, initially we need to introduce strict preference utility functions. These utility functions are such that, for every type, there is no pair of outcomes providing the same utility. In other words, the utility is specifying a preference relation that is a strict order over the outcome for every possible types of the player. The G-bar-Satterwhite impossibility result states that, given a social choice function, if we have at least 3 outcomes, and the function is onto, that is, every outcome of X can be returned by the social choice function for an opportune profile of types. And finally, the third assumption, that the utility functions are strict preference. Then, the social choice function is dominant strategy incentive compatible if and only if it is dictatorial. That is, if the 3 assumptions of G-bar-Satterwhite hold, then we can produce an incentive compatible social choice function if and only if it is dictatorial. This result is negative, showing that generically only extremely simple social choice functions can be implemented. Furthermore, these social choice functions are not interesting in economic settings. Mechanics design is mainly focused on finding positive results, relaxing one of the 3 assumptions of the G-bar-Satterwhite, and producing mechanisms that can implement social choice functions that are interesting and different from the dictatorial ones.